Okay, and yeah. Hi everyone, and welcome to my thesis defense. Thanks for taking time out of your workday to drop by in person, and thanks to everyone who has joined on the Zoom call as well. My name is Vishrant. I'm going to talk about information freshness for monitoring and control over wireless networks. This is work that I've done for the past 4 years. Yeah, I've squeezed it into 45 minutes. Let's see how much we can get through. Okay, so my talk will be divided into 4 parts. The first part will be simply an introduction. I will introduce the idea of something called the age of information, which is essentially a network performance metric. I will discuss why this metric is important, why we should study it, and how it relates to monitoring and control problems. Using this introduction, I will then introduce in part 2 something called functions of age of information, and we will ask the question, how do we optimize general functions of age of information over both single hop and multi-hop wireless networks, and essentially provide theoretical results and performance guarantees for these kinds of settings. Moving on from functions of age of information, we will then ask, well, what happens if you want to optimize functions of age of information, but you don't know the function that you're optimizing? Can you learn these functions in an online manner, possibly with time varying and adversarial settings? Once we have covered part 2 and part 3, which will be largely theoretical, we'll move on to applications, where we'll apply the theoretical frameworks that we have built to problems in robotics, notably 2 problems. The first one will essentially be a simulation problem, where we'll look at multi-agent mapping in a time-varying environment and see how to collect maps that are as fresh as possible. In the second problem, which is real experiments, we will show that instead of using Wi-Fi, if you use insights from age of information to design wireless systems, you can design multi-UAV experiments that perform much, much better than standard networking tools. So yeah, a high-level description of what we are going to do. Let's get started with part 1. So introduction, what is age of information? At a high level, think of a source that is trying to send packets over some network to a destination. Typical network performance metrics include things like throughput or delay. Throughput simply measures how many number of packets can the source send to the destination over some fixed time window. Delay measures how long each packet takes to travel across the network to the destination. Age of information is slightly different. It is a destination-centric metric. So it measures how fresh the information at the destination is compared to the information at the source. So if the source sent a packet right now and it completely went through the network immediately, then the information at the destination would be fresh, right, at that instant. Then after some time, if the source did not send any packet, then the information at the destination just keeps getting staler and staler until a new packet gets delivered, and then the information freshness again is better. This is what is captured by age of information, and at a high level, this plot describes the mechanism that I just described. So think of the source generating a packet at time t1. This packet travels through the network and reaches the destination at a time t1 prime. At this particular instant, the destination has information that is t1 prime minus t1 old. So that is the level of information freshness currently in the network. For the next few time instants, there's no packet being delivered, so the information just keeps getting staler and staler. What that means is that the age of information keeps increasing. A second packet gets generated by the source at time t2. It gets delivered at time t2 prime. The age of information now drops to t2 prime minus t2, because now we again have fresh information regarding the source at the destination. This sawtooth waveform is a typical graph in almost all age of information papers that have appeared over the past decade. The goal of age of information papers in general is to keep this age of information process as small as possible, because low age of information implies fresher information at the destination, which in turn should imply better system performance and better application performance. Okay, but why should we study age of information? There are certain applications, notably real-time applications, where optimizing age of information is really the thing that you're interested in terms of system performance. So typical examples include sensing. You want to do real-time sensing, collect information about different phenomena that are happening in real time. You want to do network control of robots. You really need fresh information about the robots to actually do control. You want to do vehicle-to-vehicle communication. Things will collide if you're not doing information that is fresh enough. If you want to do real-time surveillance, if you want to do monitoring of processes that are evolving in real time. Any of these kinds of applications essentially require freshness of information at the monitor or controller to be able to do decision-making. And age of information formalizes this notion of freshness and what it means to optimize for information freshness. And the hope is that low age of information will lead to fresher information, which will lead to better performance and better system design. And this is kind of the trajectory that we'll go through our talk. So age of information is not something that we came up with. Age of information is a fairly well-known and well-developed topic at this point. There has now been almost a decade's worth of work in the topic. And one of the people who proposed age of information is on the Zoom call, Professor Yates. So Paul and Yates proposed age of information in 2012-13 in their paper. And since then, there has been an explosion in the topic. People in theory have been very excited about the idea and applied it to many different fields. It started with queuing and analysis, moved to scheduling for wireless. People started applying it to network control, AI and learning, sampling, remote estimation, source and channel coding. There has been just a plethora of work in the field. My specific work lies primarily in scheduling for wireless networks, with applications to network control, remote estimation, and some flavors of AI and learning. And the main applications of our theoretical frameworks are to robotics and edge computing. Again, there's a huge, wide variety of age of information papers that exist. I'm not going to be able to review all of them for the sake of the time constraints. However, Professor Yinsun maintains a very nice webpage, which lists the entire ongoing history of age of information with every paper that has ever been published, categorized by all of these blocks. So I encourage you to look at the webpage to see interesting papers to read. Yeah. Okay, so that was a nice warm-up. Let's get into more theoretical parts of the topic. But again, with a warm-up. So the way we will set up monitoring and control problems is through a simple linear time invariant system. So the linear time invariant system simply evolves as xt plus 1 is equal to axt plus wt, where wt is multivariate noise. You have seen these kinds of systems in signals and systems classes, control theory classes in undergrad. So there is this source that is evolving over time. And there is a monitor that is interested in observing the state of the source, namely xt, as accurately as possible. However, the source and the monitor are separated by a wireless channel. And the channel is costly. So the monitor cannot observe the source in all time slots. It only observes the source in some time slots. And in the time slot that it doesn't observe the source, it extrapolates the trajectory of the source and maintains estimates based on the previously received samples. We call these estimates X-hat-of-T. And the goal of this entire monitoring problem is to minimize the monitoring error, which is the gap between the original process and the estimated process of the controller, plus the monitoring cost. So the source can decide, okay, I will pay cost C and observe the status of the source exactly. Or the monitor can decide, I won't pay the cost C and incur some cost in terms of monitoring error instead of paying the cost for actually monitoring and using the wireless channel. So these are the two choices that the source has. An interesting observation that we make in this very simple model is that if the last update at the monitor was received tau time slots ago, then the expected monitoring error, which is the gap between the current status of the source and the current estimate, is simply a function of tau. Now note what tau is. Tau is precisely the age of information. So what we are saying is that if you want to do monitoring of a linear time invariant source over a costly wireless channel, then minimizing monitoring error is actually equivalent to minimizing this weird function of age of information, where this function is simply a parameter of the matrices A and sigma, which just describe the underlying dynamics of the system. Interestingly, if the matrix A has eigenvalues that are outside the unit circle, then this function will grow exponentially with the age of information. If the eigenvalues are inside the unit circle, then the function will grow sublinearly. If the eigenvalues are on the unit circle, then this function will grow linearly with the age of information. So the dynamics control how quickly or slowly the function of age of information grows. And this general observation leads us to a more abstract formulation that we solve and formulate. So we generalize this idea to an n source setting. Now you have a single hop wireless network with n sources, all of them trying to send updates over a congested wireless channel to a base station. The interesting part is that only one source can talk to the base station at any given time. The base station needs to decide which source gets to talk at any given time slots. So that is the scheduling policy. And how do we design or optimize the scheduling policy? We optimize for the sum of the function of the age of information across all sources. So each source has some underlying dynamics. Depending on how slow or fast it is captured in the function. AI of T represents how long it has been since a particular source I talked to the base station. And if we optimize for the sum over the function of the age of information across all sources, we are in some ways optimizing for information freshness across the entire network. Now, the interesting part comes in, well, how do we solve this problem? We formulated it. It sounds nice. It sounds like a reasonable way to optimize for information freshness for monitoring and control applications. How do we solve it? Well, this problem, interestingly, has some very nice structure. It can be converted into something called the restless multi-arm bandit problem. Restless multi-arm bandit problems have been studied in operations research communities since the 50s. And in the 80s, Whittle came up with this nice low complexity heuristic solution for certain classes of restless multi-arm bandit problems called the Whittle-Index. The general steps involved in finding a Whittle-Index for your particular restless multi-arm bandit problem are fairly straightforward. What you do is you first observe that your problem is in fact a restless multi-arm bandit problem. You use a Lagrangian relaxation to formulate something called the decoupled problem. The Lagrangian relaxation here essentially relaxes the constraint that you can only observe one source at a time. So instead of saying you observe one source at a time, you say, oh, I can observe one source on average over the entire time horizon. This allows you to do something called decoupling. Once you have the decoupled problem, you establish a special mathematical property called indexability. That mathematical property allows you to derive nice functional forms for something called the Whittle-Index, which leads to a nice scheduling policy. We'll go through some of these steps in detail. We won't go through some of these steps in detail, but you'll see later. Okay, so what exactly is indexability? So Whittle proposed this idea of indexability in the 1980s, and it is essentially the idea of monotonicity, but slightly generalized. So going back to the single source problem, think of the cost for observing the source across the wireless channel. If the cost is fixed, typically a good policy would be something like, I will observe the source every time its information is staler than, say, 10 seconds, whatever that threshold might be. Now, if I increase the cost, my threshold should also increase. And this idea of monotonicity is precisely the idea of indexability. So if I increase my observation cost, I should only observe the source once its information staleness is, say, higher than 11 seconds instead of 10 seconds, which was true for the earlier lower cost. And we are able to show indexability for our problem. And in fact, once you have indexability, you can compute the index functions. The index functions essentially denote how valuable it is at any given time to schedule a particular source. Once you have these index functions, you can simply calculate how valuable it is to schedule any source at any given point of time. And once you have that, you can just choose the source that is the most valuable. And that gives you a scheduling policy. Okay, so we do. Yeah, so the restless part of the multi-arm bandit is because of the fact that in a normal multi-arm bandit, it evolves as a Markov chain when you're pulling the arm, but it stays fixed when you're not pulling the arm. In a restless multi-arm bandit, it evolves as a Markov chain even when you're not pulling the arm. And so restless multi-arm bandit problems are NP complete. Professor Sitsiklis and Tripathi had a paper in like 90s that proved that, but multi-arm bandit problems are easy to solve. So restless multi-arm bandit problems, even if you know all of the Markov chains, even if you know everything is known, it's still hard to solve. So the Whittle solution is actually an approximation technique. You don't want to do dynamic programming. Even if you know the entire restless multi-arm bandit, you can't do dynamic programming because of dimensionality. So you instead do this approximation that decouples the problem and you don't have to do the dimensional thing. So yeah. Okay. So yeah, we established the fact that the functions of the age of information problem is indexable. And we derive these nice functions for the Whittle-Index given FIs. So FIs were our original functions of age of information. We use those to compute WIs, which are the Whittle-Index functions. Now, this expression might look complicated, but it has a nice intuitive explanation. So think of this rectangle in this plot. On the x-axis, I'm plotting age. On the y-axis, I'm plotting cost. And the blue curve represents the function of age of information. The Whittle-Index W is the area shaded in yellow. So if this blue curve was growing very quickly, this yellow part would be large. If the blue curve was growing slowly, this yellow part would be small. So it really captures how quickly or slowly the function grows with the age of information. And that's why it is somehow the right index for doing scheduling. And once you have these Whittle indices, as I said, the scheduling policy becomes obvious. It's simply the maximum over all sources of the Whittle index of the age of information. That's it. Choose the source that you think is the most valuable. Okay, so we have this nice solution to it. What kind of performance guarantees can we give? Can we say that this is optimal? Well, no, things don't work out as nicely always. So yeah, typically the Whittle index is not optimal. In prior works over the past 30, 40 years, since Whittle proposed his index, people have shown Whittle index to be optimal in two kinds of systems, either symmetric systems, where all of the functions of age of information, for example, would be identical, or in the limit as the system size grows to infinity using a fluid limit approach. What we felt was that both of these have gaps. So what we wanted to do was actually show optimality of the Whittle index for a finite and asymmetric system. And we were able to show this for a small system with two sources. For two sources with arbitrary functions of age of information that are increasing, we were able to show that the Whittle index is actually optimal. We were also able to show that some index policy, not necessarily the Whittle index, but some index policy, I will precisely define what an index policy means on the next slide, is optimal for the three-source problem. Through simulation, we were able to show that for n equal to 4, the Whittle index policy is not exactly optimal. So we found a counterexample, but the gap between optimality is small. Through further simulation, we were able to show that for general n, the Whittle index policy is actually very, very good. And that's why it is a very good solution, because the exact optimal policy is very hard to compute and very computationally involved. The Whittle policy gets you very close to optimality, but is very easy to compute, as long as you can establish indexability. And that is the reason we go through this entire process of the recipe of creating the Whittle index and deriving the Whittle index functions. Okay, so how did we prove this finite asymmetric system result? I provided a quick recipe for this proof. The first thing that we did was define something called strong switch type policies. The mathematical description is a bit complicated, so I won't go over it, but the idea is explained in this picture. So think of a scenario where there are 4 sources, and the current age of those sources is A1, A2, A3, and A4. So A2 has the largest age. You decide at this point that you schedule source 2. Suppose that the functions are such that you decided to schedule source 2. Now, you encounter another scenario where the ages of the sources are A1 prime, A2 prime, which is greater than A2, A3 prime, and A4 prime. What you observe is that the information for source 2 is tailored. The information for sources 1, 3, and 4 is fresher. So clearly, if in the previous scenario you decided to observe source 2, you should make the same decision to observe the source 2 again. It seems like an intuitively natural property that an optimal policy should have. It's kind of encoding the same monotonicity structure that indexability has. So we wanted this nice strong switch type property to apply to policies, and all policies that satisfy this strong switch type property, we define as strong switch type policies. But we then were able to show that there exists an optimal policy that indeed satisfies this strong switch type property. So this is, which we thought of as an intuitively nice property, is actually truly a signifier of optimality. We then define something called index policies, a completely separate definition. These are policies that look like Whittle index policies, but not necessarily with Whittle index functions. So you create some arbitrary monotone functions, f1 up to fn, and you design a policy that simply states, choose the source that has the highest value among fi of ai, where ai is the age of information of source type. Very different class of policies. What we were able to show was that strong switch type policies and index policies are exactly the same. These are equivalent classes of policies. What this means is now that there exists an index type policy that is optimal, because strong switch type policies, there is an optimal policy. Finally, what we were able to show was that among the class of index policies, for n equal to 2, Whittle index is the best index. What that means, going back, is that Whittle index is the best index policy. Index policies are the same as strong switch type policies. So Whittle index is the best strong switch type policy. But there exists an optimal policy that is strong switch type, so Whittle index must be optimal. And this proves that Whittle index must be optimal for n equal to 2 setting. Quick recipe. I found this proof to be nice because it can be applied to other restless multi-unbounded settings, and people haven't observed these kind of proofs before for finite asymmetric systems. Okay, so this finishes our single hop wireless network setting. What we wanted to do next was extend our results to multi-hop wireless networks. So think of multiple wireless links and the source being one trying to send packets to say no.
Sorry,
yeah.
Just understand.
Sure.
Okay, here we only consider variables, right?
Yes. So some of these results are truer for larger n.
Punchline is block code here, right? Like that's the main result of this.
I would say the punchline is more that there exists an optimal policy of strong switch type, because that was something that had not been observed before. That is a fairly strong structural result. So I feel like this already implies something very strong about some optimal policies, meaning that they have nice structure. So that limits the space in which you need to search.
Okay.
Yeah. Whittle index is just one of those with nice structure that tends to work pretty well.
By the way, I'm also a bit confused in your, like, okay, there's no entire.
I have randomness, I kind of gloss over it. So the channels are technically with some probability of reliability. So you can get packet drops and you can incorporate it into the model and do the entire analysis and do everything with it.
Okay,
Yeah.
so, but I mean, okay, so that's,
Yeah.
Given the states, right?
Mm-hmm.
Okay, so you're in multi-arm bandits.
Yes.
Exploration, right?
So that's the thing with multi-arm bandits, because you are learning something that is unknown, you have to do exploration. There's nothing unknown here. Everything is known.
That's what I'm trying to understand here.
So we will do learning in part 3.
But since there's no exploration here.
Yes.
Okay, so that's just a computational issue, right?
The issue is you can't do dynamic programming, so you need to do something better than dynamic programming.
Why you can't do that?
Because of cursive dimensionality. So once you have like 10,000 sources, you can't find the optimal policy.
Yeah, you can do some neural net estimations.
Well, typically not really. Things can change in real time. Like these functions, for example, in part 3, that is what you'll find is that if these functions start changing over time horizon, then you will need to retrain everything. And basically, like you can't provide performance guarantees, you can't do theory. So the goal of this is
theory, but okay, if you pay me money to solve this, I would just slap by neural nets,
Yes.
Do you have indication of this plan? Let's say to achieve 99% of the.
So one of the, I would say, things that people have seen in queuing networks and wireless networks in general has been, at least for the longest time, that throwing neural networks at the problem doesn't tend to work. What we have seen is that policies that have structured things like max rate for throughput optimality, you can't do throughput optimality with queuing networks even now. So you try to throw deep reinforcement learning at a queuing network problem, people have not been able to figure out how to do that yet.
So
yes.
Even if you restrict the policies, which I will say in this type.
I think then, yes, things start becoming easier. You will probably still end up with the Whittle-Index, something like that. So
and at least that works for and
yes, I would say that the computational effort that you would put in training the neural network would probably still be more than just explicitly computing the Whittle-Index function and putting in this policy. This policy is just very easy to compute.
No, I understand that once you have, I mean, it's of course very easy, but the thing is, I'm just trying to understand the value of proving that it's optimal.
Yes.
Like if like something that like first year called out typically is optimal, but you're saying typically is very bad.
We would expect it to be very bad unless you give it structural information.
Okay.
Yeah. Yes. Okay. So I think that's something that you would see even further in the multi-hop problem. So once you have multi-hop links, unicast, multicast, and broadcast flows, and you still want to optimize functions of age of information, what you need to do is now choose both scheduling. So which link gets scheduled at any given time to prevent interference, and also routing. So what paths do packets take to reach destinations? Typically, this is a problem that has remained unsolved. So even delay optimal multi-hop routing and scheduling has not been solved yet. What we propose in this setting is something called HDET. This is an algorithm that we propose, inspired by Lyapunov-style network control. However, this is slightly different than Lyapunov-style control. So the way I consider Lyapunov-style network control is that it is a proportional controller of a queuing network. And you can instead do a proportional integral controller, for people who are familiar with PI control, of a queuing network. And once you do proportional integral control, you start to get nice age performance. So the entire idea of HDET is trying to do PI control of a queuing network around a fixed set point. This is a heuristic approach, but through simulations, what we were able to show is that for any single hop or multi-hop setting that has been studied in age of information literature over the past decade, our HDET approach actually either matches the best known theoretical result or outperforms it. So it is, for now, the best known multi-hop scheduling and routing scheme for wireless networks and age of information. Not too much theory, but a nice heuristic algorithm. Okay, so that covers single hop and multi-hop wireless networks when you know the functions that you're going to optimize. Okay, what if you don't know the function that you're going to optimize? Typically, age of information, as I said, is a proxy for monitoring or control performance, right? So we assume that the functions fi are known beforehand, they remain fixed throughout over the horizon that you're optimizing, and they are a good proxy for the monitoring or control cost. What if this age of information to cost mapping is not known in advance, possibly time varying, and possibly adversarial? So what if the dynamics of the system sometimes are fast or sometimes are slow? If the system becomes fast, then you should give it more priority. If the system becomes slow, then you should give it low priority because its state is not changing as much. right? How do you adapt to these kinds of changes in the situation? So the way we tried to address this was we went back to the restless multi-arm bandit and tried to formulate an online learning formulation for the general class of restless multi-arm bandits, something that we found had also not been done in literature before. So the way we did it was through an episodic setting. At the beginning of the episode, you choose a scheduling policy. That scheduling policy runs over a particular instance of a restless multi-arm bandit problem. That restless multi-arm bandit problem remains fixed for the entire episode. As the episode ends, you receive a new restless multi-arm bandit problem instance, and you choose a new scheduling policy. Between these two episodes, the restless multi-arm bandit problem instance can change arbitrarily in a time-varying manner and possibly adversarially. The goal of the scheduler is to adapt the scheduling policy to the changes in the restless multi-arm bandit problems it keeps receiving over these episodes. Each episode is of length m, which is fairly large. So you fix the scheduling policy for a fairly large time horizon, and then you update your scheduling policy based on things that you learned about behavior in the past. Okay, we assume that the cost functions of age of information will change across episodes arbitrarily, but remain fixed within an episode. However, they change such that they maintain indexability or monotonicity, so that we can apply all of the Whittle discussion that we just had. Okay, so the main question that we ask is, can we design a scheme that can incorporate all of the changes in the environment in an online manner and learn from what is happening to these sources to design a scheduling policy that can adapt to changes in the environment? And the answer is yes. And we can actually provide nice performance guarantees, theoretical performance guarantees for it. However, you can't just directly apply standard online learning algorithms to it. And the next slide should discuss that. So you can interpret the problem that we have just formulated, the online learning formulation problem, as a classical online learning problem called learning from experts. Learning from experts is simply a problem where you say, oh, you have n experts. Each expert gives you a particular reward, but the reward for each expert changes arbitrarily across episodes. Which expert should I choose? Which will give me the most reward on average across the entire time horizon. The standard way to solve learning from experts is by something called follow-the-perturbed leader. This is a classic online learning algorithm that has been known since the 1930s. It has 3 steps. You maintain the sum of rewards that you have observed for each expert in the past history. You perturb this history of rewards for each expert by a slight amount. The way the perturbation happens is in an independent and identical manner. And once you have perturbed it, you find the best expert using this perturbed history. The way our problem is similar to learning from experts is that you can think of experts as scheduling policies. At the beginning of each epoch, you're choosing a scheduling policy. You receive some feedback about its performance, then you choose a new scheduling policy. You receive feedback about the performance, you choose a new scheduling policy, right? The problem is the number of scheduling policies scales exponentially in the length of the epoch and also polynomially in the number of sources in the network. So n to the power m. If m is large and n is large, this is a very bad number. You can't do follow the perturbed leader in a computationally efficient manner for this scale of a problem. You can't make IID perturbations for these many numbers. You can't maintain the entire history because you have to store these many numbers. You can't find the best policy because you have to look at all of these policies. Recall that finding the best policy problem is the same as the thing that we discussed in part 2. Given a fixed function of age of information, finding the best policy means finding the policy that solves the functions of age problem optimally. We don't know how to do that. We know how to solve it almost optimally using the Whittle-Index approach. So traditional online learning methods in this setting are infeasible. We need to do something else. What we do is we create something called Follow-the-Perturbed-Whittle-Index. And the 2 key ideas are, instead of finding the exactly optimal policy in each epoch, use the Whittle-Index as a low complexity optimization oracle. So in step 3, instead of saying find the best policy, you say find the Whittle policy. And instead of perturbing the cost for each scheduling policy, so perturbing the cost per expert, you actually perturb the cost for the reward functions themselves. The reward functions are only n cross m instead of n to the power m, so much lower dimensional space. However, these 2 key ideas create new challenges for regret analysis. Clearly, the perturbations need to maintain indexability, otherwise you can't use the Whittle-Index. However, if you create perturbations to maintain indexability, they are no longer IID for expert or scheduling policy, which is a crucial requirement for regret analysis for follow-the-perturbed leader in classical online learning. And the Whittle-Index is only an approximate minimizer, as we have seen, not an exact minimizer. So our main contribution is resolving these 3 technical challenges and still having some kind of regret guarantees. And our algorithm looks like this. This is fairly complicated, but there are three key parts. The first part is monotone perturbations that ensure indexability. This resolves the first challenge. The Whittle scheduling, as I said, replaces the optimal scheduling, so there's no computational issues now. And we maintain the entire history, but we maintain the history using only the cost functions, not for the scheduling policies themselves. So again, a loaded dimensional space. Okay, so what kind of regret results do we have? The regret results we have are essentially in terms of a linear term in the number of episodes plus a sublinear term in the number of episodes. Now, if you know anything about regret, you will say, well, this is not a good regret result because there's a linear term plus a sublinear term, the linear term dominates. However, the linear term with the coefficient in front of it is alpha. And alpha is a parameter that measures how close the Whittle index is to the optimal solution. So this is the cost that you are paying for choosing a heuristic optimizer instead of an exact optimizer. You can't get away with not paying this cost unless you try to go for exact optimality and do dynamic programming and pay the curse of dimensionality. So what this regret result is saying is that compared to the best Whittle policy that could adapt in an online learning manner, you're actually only paying sublinear regret. Or if you had two sources and alpha was 0, we are paying sublinear regret compared to the best optimal policy as well. We know that alpha is small, so this term typically would tend to be small as well. Okay, so that completes our online learning section.
Sorry.
Yeah, of course.
So you mentioned FTL.
Yes.
Computationally complex, but well, they don't care about complexity. So is there a bound on regret?
The bound on regret would also be much worse. So here we have MNT, right? Everything here would be like n to the power MT.
Right, but that's maybe that's just
it'll still be a scaling constant, yeah.
I understand, but is it probably okay? So let's okay. I think when the human looks for let's say it's not and the variable by blah, should by blah, but it's computationally complex, so that will give you a low complex number.
Yes.
Here it seems like you're saying there's no lower bound.
We don't know the lower bound. Yeah.
There's 0 lower bounds.
Yeah.
And you say then okay, then I think you should be careful about you should say like okay, I'm proving the regret bound in addition to my algorithm is actually also computationally feasible.
Yes.
Because you were saying okay. Interesting.
So compared to the best fixed Whittle policy, this will give you sublinear regret. That's all I'm saying. I'm not saying that it will give you optimal regret.
You're saying the best regret, let's say, I mean, involved is pretty low.
So I would say that you have to pay this alpha t if you are doing some approximation. If you're not doing approximation, only then you will get away with it. Because NP, because restless multi-parameter problems are known to be NP-complete, you cannot get away with not paying alpha t unless you do dynamic programming.
I mean, I didn't understand the setup of the problem very well, but
okay.
Don't worry,
okay.
I just wanted to, I think it's a good opportunity for you to try to go lower.
Yeah. Yeah, I think because the setting was also created by us, people haven't really looked at this kind of online learning for restless multi-arm bandits before. Like restless multi-arm bandits problems have not received that much literature, like focus in learning literature. So
well, I mean, they're pretty flexible.
So the problem is that restless multi-arm bandit problems cannot be solved even when everything is known. So once you add learning, it just becomes even more complicated. So people tend to focus on multi-arm bandits instead of restless multi-arm bandits.
Right. I mean, they're upper lower bounds in terms of saying.
Yeah. So typically, when people do learning for restless multi-arm bandit problems, they just do reinforcement learning because the optimal way is dynamic programming. So you will do reinforcement learning instead of that. So
I'm just saying, like, I'm less than practice.
So even for regret, people will do reinforcement learning. They will try to do reinforcement learning for restless multi-arm bandit problems and then try to prove something about it. But then the reinforcement learning methods are computationally infeasible to implement for large restless multi-arm bandit problems. Yeah, so it's like restless multi-arm bandit problems are just a special case of MDPs with some nice structure. So they are hard to solve.
Yeah, but they're also like upper lower bounds, right?
Yes. So interestingly, for restless multi-arm bandit problems, I don't know of like special lower bounds that use the structure.
But maybe you don't need the structure.
Okay, yeah, that's possible. Yeah, we know that for performance guarantees, using the structure helps to derive some of these performance guarantees, and for computational feasibility, the structure information helps a lot. Like if you don't utilize the structure, you cannot build tools that are computationally feasible to implement in, say, a base station or a Wi-Fi router. So, yeah, which is what we will do at the end. So, yeah, so applications. The first application that we will consider is a completely simulation-based setup. So think of robots that are moving around and mapping different rooms. So the blue dots are robots. They're collecting LiDAR scans. Each of these is a room. The black portions of the map are obstacles. And these obstacles appear and disappear in these maps in some time-varying manner. The way that we choose is through Markov chains. So the cells turn on and off with some fixed probability over time, right? The goal of the robots is to collect as accurate a map of the environment as possible, and then transmit this map over a congested wireless channel to the base station. The base station is interested in knowing the maps of all of the rooms at all times. The metric through which we measure the accuracy of the maps is the entropy. The entropy becomes worse and worse the longer the base station has not received any update about the map. So this is like an age of information setting. We convert entropy to a function of age of information and apply our Whittle-Index framework to show that instead of standard networking, if you use a function of age of information framework, then you can have much better monitoring accuracy and much better system performance for this kind of a monitoring context. We add one layer of complexity to all of this in addition to part 2. We say that the robots can find the LiDAR maps in different resolutions. So they can create the LiDAR maps in different resolutions. And you can control whether to generate a high resolution map that takes longer to send or a low resolution map that is quick to generate and also quick to send. And we'll have some nice insight about controlling this resolution as well. And the way we will show this is through a video demonstration. So there are two things to notice in the video demonstration. The first one is that the top one includes the optimization of the local resolution, the processing time, and our proposed Whittle-Index scheduling. The bottom simulation will show the baseline processing, so a fixed low resolution being sent, and randomized scheduling. So scheduling has not been optimized. This is how Wi-Fi works. Wi-Fi is typically something like randomized scheduling. And there are 3 columns here. The first one is the actual map. So once I run the video, you will see obstacles appearing and disappearing with some probability over time. The middle one is the actual location of the robots as they do random walks in their rooms and update their LiDAR maps. The final one is the estimated map at the base station based on the updates it receives from the robots. The longer the base station does not receive an update from a robot, the more gray the grids of the cell become because the information has grown stable. And what you will notice is that there will be more gray here, less gray here, and that's the key highlight. So let's play the video. So for quickly varying regions, which are these, the blue ones, what we observe is that you should keep sending low resolution maps, because if you spend time to generate a high resolution map, the region would have changed by the time you generated the high resolution map. For slowly varying regions, you should actually put in the time to generate high resolution maps and then send them less infrequently. So you should basically spend a lot of time, create an accurate map, and then when you get a chance, you send the entire map, because the region would not have changed by the time you generated this high resolution map. And that is what you will see here. The maps generated here are much higher quality than the maps generated here. So basically, both of these aspects are practical aspects when you're trying to do LiDAR mapping with multiple robots. And you can create a framework to optimize both resolutions and wireless scheduling to do much better monitoring. But this is still a simulation. It had some assumptions. This was MATLAB LiDAR sensors. It was not real LiDAR sensors. So the final thing that I did during my PhD was trying to implement all of the learnings that we had from our theoretical frameworks into a real robotic systems and see if we can build a real system that can show significant performance improvement over standard networking solutions. And so this has been the long promise of age of information for a long time. And what we did was we built this system called YSwarm that actually showed that, yes, compared to Wi-Fi for multi-agent robotics, you can actually build a system that incorporates age of information-based ideas to design much better and much more scalable systems to perform real-time tasks. And the main task that we showed our application for was this thing called mobility tracking. So it's a simple idea. It's mobile objects moving around on a floor, and each mobile object needs to be tracked by a UAV. However, the UAVs themselves are not intelligent, so they don't have too much computation on board. What they can do is they have sensing, so they can collect video of cameras facing downwards, and they can send these video frames to a central base station that can do the compute and send back information to the drone. Okay, your target is moving left, so you should move left. Your target is moving right, so you should move right, and so on. So really, age of information becomes a very crucial thing to optimize here. If the video frames being sent are delayed, then by the time you actually receive control commands to move, your target would have moved outside of field of view and you cannot do tracking in real time. This really starts happening once you have lots of UAVs trying to talk to a single base station. And again, this is something that you would want to do when you're trying to design a scalable system. Think of an Amazon warehouse where there are lots of robots trying to talk to a single Wi-Fi base station and trying to do real-time robotics tasks. The goal is to try to have fresh information at the base station so that it can send back fresh control commands so that it will have relevance when it is delivered to the robot. We did this by setting up these two pieces of hardware. The first one was these drones, which were built by Ezra and people in Seltat's group. Yeah, I had no expertise in building hardware, so this was all of their work. Some very cool stuff about these drones was that they had Raspberry Pi Zeros on top of them. If you have ever worked with Raspberry Pi Zeros, you know that they have basically no computation. They are $10 CPUs with 500 kilobyte RAM. They cannot do image processing in real time. What they can do is interface with cameras. So we had the cameras pointing downwards and with this big Wi-Fi antenna. So they collect video, it goes to the Raspberry Pi, it goes through Wi-Fi to the base station, which does the processing and sends back control commands to tell the drone where to move. We also use these cars with these tags on top so that we could actually detect where the cars were in these video frames. And these had these tiny mocap balls, so we could actually have an accurate position estimate for our own tracking and data collection. Yeah, so this was our hardware. This was how we had designed our software system. The most interesting part about our software design was that we did everything at the application level. So we did not touch the lower layers of the networking stack at all. We wrote all of our code in Python. It was honestly a fairly inefficient implementation, but it did the job, which is what's required for a research project. So it was fine. There were three key things that we did. The first thing was actually something that has been well known in age of information literature for a very long time. It is that if you have a source that is trying to send updates to a destination, you should not have first come, first served queues. Because once a new packet arrives, all of the packets that are sitting in the buffer of the queue are actually old. They're useless. You should not transmit them. So you should have a last come, first served queue. Replace all of the packets that are in the buffer every time a new packet is generated. So we implemented this at all of the drones so that every time a new video frame is generated, you replace all of the old video frames. We then implemented our Whittle-Index scheduler at the base station so that it tells each drone, okay, you talk now, you talk now, you talk now, so as to completely eliminate interference that is typical in Wi-Fi networks with multiple things trying to talk at the same time. So we had no interference. And we also incorporated the online learning scheme so as to be able to learn which targets are moving fast at any given time. If the targets that the drones are tracking are moving fast, they should have more priority. They should send more video frames. And if the targets are basically stationary, you don't need to send video frames. You don't need to spend channel capacity on tracking these slow moving objects. However, we programmed the cars to move randomly. So sometimes they would be fast and sometimes they would be slow. So you had to learn this aspect of the environment in an online manner. So we incorporated both the Whittle-Index scheduler and the online aspect together in this system. And now some interesting results. So our baseline system was essentially first come, first served queues or FIFO queues with Wi-Fi and UDP. So standard networking protocol, nothing being changed. If you just took things off the shelf and tried to implement multi-UAV mobility tracking, what we got was at most 2 targets could be tracked at any given time. You could not do 3 drone tracking using Wi-Fi. So it did not perform well. The age of information was fairly high. It was 0.2 seconds, and the tracking error was very large. It was almost 2 meters. With our system, which had last come first served queues and Whittle scheduling, we were able to track at least 5 targets at any given time in parallel. This was because we only built 5 UAVs. If we had more UAVs, I think this number could have gone larger. And we broke 1 UAV. Yeah. And our average AOI was better than what Wi-Fi achieved for 2 drones. Our tracking error was 5 times better than what Wi-Fi achieved for 2 drones. So almost an order of magnitude performance improvement, despite everything being implemented at application layer in Python. We believe that if someone implements the learnings that we have made through our theoretical frameworks into a Mac layer scheduler and builds a new Wi-Fi chip for age of information, they could probably get another order of magnitude performance improvement and scalability. So yeah, future blueprint. Probably the most fun part of the talk, I will give some video demonstrations of the multi-drone flight experiments. Okay, so you will see 5 drones trying to fly over the space and tracking these 5 cars. These video animations are thanks to Ezra, and we spent many nights together in the lab trying to get the system to work. So yeah, I'll just stop the video here for a bit to explain what's happening. Okay. So there are three things being plotted here. The first one is the actual 2D location of the UAVs marked as X's and the cars marked as squares. So basically you can see the UAVs flying here, the cars flying here. We are plotting the age of information, which drops when a UAV sends a new packet. It keeps increasing when the UAVs don't send a packet. We're also tracking the mean tracking error across these two targets. And this is Wi-Fi. So what you will see is that the age of information is pretty bad. The tracking is not very good, and the error is fairly high. I'll start the video again. So Wi-Fi kind of works, but not really. It has issues. So it will recover a bit, then things will go out of the field of view, then it will recover a bit. And the tracking error sometimes becomes very bad. So for example, this was just lost. Now this is our system for 2 drones. You will see the tracking is almost perfect once this starts moving. There's perfect tracking, much better age of information, much lower tracking error. And this is just for 2 drones. And as soon as this part of the video ends, you will see 5 drones doing the same thing. So again, almost perfect tracking for 5 drones, 5 targets. Still, the age of information is not too bad. Sometimes there are packet losses, but it is a wireless system, so there will be packet losses. Very low tracking error. So we are able to do much more. We are able to build much more scalable systems because of the insights that we have from theory. So the goal was to derive some theoretical insights, but then also build a system that can implement those and see if all of the things that we claim in our proofs actually, and we were able to show some of those. Yeah, so there were 2 other things that I did over the past year in my PhD. I won't really spend too much time on them because of time constraints, so I'll just provide 1 slide each for them. So one of the things that has been known in age of information literature for fairly long is that people typically work on problems that assume that the information from different sources is uncorrelated or independent. So when source 1 sends an update and source 2 sends an update, there is no common information between them. So only the age of information of 1 drops when 1 sends an update, and only the age of information of 2 drops when 2 sends an update. But what if 1 and 2 were observing something that was correlated? Suppose they were cameras that had an overlapping field of view. Can you utilize this correlation structure to design better scheduling policies? Can you still provide performance guarantees? And is studying this correlation actually important? So we made a simplistic model to understand correlation in these kinds of settings, and derived some nice theoretical results on this, which we published in MobiHawk. This paper actually won a Best Paper Runner-Up award. But yeah, I don't have time, but I'm happy to take questions offline for this paper later. The other thing that you will have seen throughout this talk was this discussion on scheduling policies. And all of these scheduling policies that I was talking about were centralized. So I was telling the base station is going to decide source 1 gets to transmit, source 2 gets to transmit, source 3 gets to transmit, and so on. All of these centralized scheduling policies require some support for polling. So they require the base station to decide who gets to transmit and when they get to transmit. What happens if you don't have this support? Can you design distributed protocols like the way Wi-Fi works, but modify the way in which Wi-Fi works so as to still have age of information guarantees instead of throughput guarantees, which Wi-Fi has? We were able to show that, yes, you can do that. Interestingly, the way CSMA works is by sampling random timers. So if 2 sources collide at any given time, each of them samples a random number. And once this random, and they start these random timers. So they start these random clocks. Once this random clock ends, they probe the channel again. If the channel is empty, they will start transmitting. However, these random timers are sampled in a specific way in the 802.11 protocol. We claim that if you can change the way in which these timers are sampled, you can actually derive very nice performance guarantees and optimize for age of information just by this tiny change in the CSMA protocol. So this is a fairly interesting result. It basically claims that you actually don't need to do the centralized base station polling thing and still give nice guarantees. The only thing you need to do is change the way in which Wi-Fi works, or provide another option in the way in which Wi-Fi is configured in typical systems. Okay, and that's all of it. So I will stop for now for questions, and then I will go for it.
Thank you.
Thanks.
So questions, and what I want to do is before we take questions from the audience, live or online, I would like to start with questions from the Thesis committee, who are all today online.
Yes.
So I don't want to call on anybody in person then already, but one of the Johns, perhaps, John Howe or John Tsitsiklis, one of you, any questions?
Okay, let me ask a very high level question. So what one is really interested in is the uncertainty in the information that you have available. So in
Yes.
many cases, the amount of uncertainty is closely related to the age. And
Yes.
conveniently, in the linear quadratic example you had in the beginning, it's the uncertainty is a deterministic function of the age.
Yep.
And if I understand right, all your work for the restless bounded framework basically focuses on just the age of information, but the more practical work towards the end
Yep.
would be where you're interested in the uncertainty itself, not the age. So
Yes.
suppose you have a situation where a measurement tells you that this vehicle is in a region where it can only move very slowly.
Mhm.
So taking that into account, I can wait a long time before I collect information.
Yes.
So for this, of course, it's a more general, more challenging class of problems. For that one, is there a general theoretic formulation that's worth studying in some generality or abstraction and hope to make progress? Or is it more case by case, depending on the application?
I think people have started looking at this. So I think there has been this trend in the age of information community now with looking at semantics and age of incorrect information and context along with age of information, and trying to incorporate these ideas into theoretical models to say, okay, certain times when the source is not changing, there's some particular context in which that happens. So if you can model that context, you can incorporate it into your optimization problem and adjust your policy based on context plus information latency.
Yeah. May I actually follow up on that then?
Yeah.
But Vishrant, what John suggested sounded to me fits into the framework of functions of age information.
Yes,
of course.
you can also do online learning and learn what happens in certain settings. So you can assume that the functions change over time.
But even if they don't, yes, they do change, fine. But what John suggested that there is one vehicle that's moving very slowly.
Mhm.
And if I know that the vehicle is moving very slowly, presumably I have to know that to make any
Yes.
wise decision. That changes the function of age. So the function of
Yes.
age now will be somehow more forgiving.
Yes.
If that's the case. So I thought that was sort of a motivation. when we
Yes.
started the function.
I think what John is saying specifically is that, for example, when the vehicle is moving here, it is moving fast. When the vehicle is moving there, it is moving slow. Then can you incorporate that particular idea that, oh, if the vehicle is localized in a particular small part of the environment, it is slow, so you don't need to give it high priority. So something like that.
Okay.
I think if I understand the question correctly.
Yeah, so it would be a function of the age of information, but that which function it is changes stochastically depending on the content of the measurements that you are getting. So unless you are in a regime, I think Eytan was suggesting a regime where that context changes very slowly. Yeah, the function changes, but you kind of know what it is.
Yes.
The
So
challenge
the online learning kind of takes care of it, but the online learning is still context independent. It's kind of a worst case assumption. But yeah, if you have more information, then you can put some stochastic modeling over that context and try to learn the evolution of the functions themselves.
Okay, thank you.
I think that is an essential question, right? I mean, that's an essential problem, but okay. Any other questions, John?
No, I'm set. Thank you.
Thank you. John Howe, do you have any?
Yeah, and thanks for a great talk. You kind of touched on this on slide 32 when you were talking about the experiments, but I'm a little fuzzy, quite frankly, on why the Wi-Fi did so badly. I mean, we work in that same room with Wi-Fi, and it's not great, but like it's not as bad as your videos sort of made it out to be honest. I mean, it's not. So I'm a little surprised why it's so poor.
That's a very good question. So the main reason is that we are sending video data. So if you're sending, say, telemetry, things like basically measuring position or velocities, it's only like a few bytes. But once you're trying to send video data, it's few kilobytes to megabytes per drone per second. There's a lot of data, a lot more congestion in the channel. That's the main reason. The second one is interference. So once a lot of drones are trying to send video data all the time, the packets keep getting collided. And so there's a lot of delay or latency in the network. And the problem with tracking is that it really is essentially a problem of information freshness. So even if you're getting reasonably high throughput, so your packets are getting delivered, say 1 second later, that's not any use to you because your target has already moved outside your field of view. So you might still be getting like good video data, but it's just old, and old video data is useful to you.
Right. But again, the reason for doing the video streaming is because you can't do the video processing on board?
Yes. So because we created this artificial situation where we put Raspberry Pi zeros on top of the drones, and we wanted to, the ideal way in which we would have showed this would have been another drone with, say, a TX2 on board, which talks to these small drones. So this would have been like micro UAVs plus a full-scale UAV, and the micro UAV stuck in the full-scale UAV. So this creates kind of a potential for scalable design with cheap drones and more expensive drones.
Well, but again, you could have put a TX2 on the drone. I mean, granted, it's a lot of computing to carry, but I mean, the point being, had you done the video processing and boiled it down to labels or semantic sort of objects, I mean, then you're only sending, kilobytes, not megabytes, right?
The point is that if you put a TX2 on board, then your drone costs $600. If you put a Raspberry Pi on board, your drone costs $50. So you can have one drone with TX2 and then 10 drones with Raspberry Pis, and you can still have a scalable system. So what we're saying is that you can design much more scalable and much more cheaper systems if you get better communication than focusing on putting computation on each drone. So
I'm not arguing with the scaling. It's more a case of like, when does this become a problem that needs to be solved? Because if you had a vehicle that could do the processing and all you're exchanging is sort of lower bandwidth data, then maybe the age is less.
Then it's not an issue as such. So the interesting part kind of becomes more when you're really trying to do real-time inference. So for us, if you actually have, say, for example, a TX2 on board, but the inference that you are doing is still very involved, what you can have is a low complexity model on board and a high complexity model on the cloud. And then you can switch between the low complexity model and the high complexity model. I think there's some interesting work coming out of Professor Alizade's group in CSAIL working on these kinds of switching contexts. And they still have a lot of information going across over the wireless channel, and they still need to do optimization.
Right. The last question, if I can, is, and I think John was getting to this point, because like slide 3 or the very beginning, you made the point that if you could do things, if it was fresher data, it would be better data or better accuracy. But new data isn't necessarily better data. So is there like some quantity which is a product of or combination of age and quality?
So that is exactly what people have been looking at in terms of age of incorrect information and age of information literature now. So we have been also looking at that more recently. So that is essentially some kind of quality of information times how old the information was when you received it, indicating how valuable the information is right now. And that kind of helps you really encapsulate this idea slightly in a more involved manner. And so people have been looking at semantics and like what matters when you're trying to convey information as well. I think there have been lots of workshops happening over the past year in semantics and age of incorrect information. So there is interest in this area. I think a few people on the call, I think Professor Sun, Professor Papas, they have been working on these ideas recently. So
And do you think that these ideas map to that measure as well, or is it just going to be completely different?
No, I think the insights that we have from optimization about age of information will also apply to problems when you're trying to optimize age of incorrect information or whatever semantic notion of information that you're trying to optimize over. I think the insights will still help. You'll probably have to do some new analysis to fit into these new frameworks, but we already have this nice theoretical framework that we can start from instead of starting from scratch. So,
great.
Yeah.
Right. Thank you very much.
Thanks.
Thank you, John. I'm going to ask you to pinpoint it and allow some of the other faculty in the meeting, especially I noticed the faculty in the Zoom call. So maybe I'll start. I see Yin. So so I see Yin. I see Nick Papas. I thought I saw
I think Roy is there.
or Yates. So please, maybe Yin, did you have questions, comments, anything?
Yes, I think I have like one question and maybe a couple of comments.
Sure.
So
Yeah.
reading Vishrant's paper, this is Bioptic paper 2021, and I
Yeah.
think that because the work you have is actually for a single channel scenario. So I'm
Yes.
wondering if this asymptotical optimality of Vito's index is that
Mhm.
really for a scenario for one channel, or is that for the scenarios where the number of users and the number of channels both grows to infinite?
The asymptotic optimality, which was proved by Matuk and Ephremides, was for a setting when the number of channels and the number of sources both grows to infinity. So the number of channels divided by the number of sources is a constant, and they scale the number of sources to infinity. So that's the paper I think I was referring to. So that is not directly applicable to our setting. It kind of just supports the idea that yes, in certain settings, the Whittle can be shown to be asymptotically optimal. We haven't observed or proved the Whittle index to be asymptotically optimal. We have only shown exact optimality for a finite asymmetric setting and not for an asymptotic setting.
Right. I think because this work you have actually is related to the length of your data and the unit.
Yes.
So I mean, if there's a way you can generalize this scenario to a multiple scenario, that'd be good. So I mean, I was lucky to have some collaborators which where on a scenario where with multiple channels extending the scenario different channel lengths. So that's one thing. So the other thing is that actually, I have been working a lot on these thresholds-based policies. First for single cell scenario, and I recently started to have results for multiple user scenario.
Yes.
Using Vito's index, and now I find it very, very interesting, which is the case. These threshold-based policies and the Vito's index fundamentally they are in the same framework.
Yeah.
So what as a comment, okay. So basically, what I observe is that if you apply Vito's index to those kind of problems, we will be able to exactly recover this kind of threshold policies in my papers. So in some sense, it's beneficial in both ways because it's also in some of these challenging problems how to really find the Vito's index.
Yes.
That's one thing that I observed. And
very good observation. I think that the intersection between kind of the Lagrangian relaxation and the single source problem, and then the multi-source problem, because they are essentially the same once you do the relaxation. So
right. That's why I'm commenting on that. So because in your problem settings, it seems to be like trivial to consider like n equal to 1. However, there are single user cases that are not trivial, and then you exactly see that these two frameworks actually combine. So I mean, when your group and my group are working on these things separately, and it's actually right now we see they are actually the same framework. So that's very interesting for me to observe. And the other thing is I could comment on is that we actually have some recent information strategy work to calculate what scenario fresh data is actually better than stale data. What scenario is actually worse than stale data. So that theoretical work, it could be like very related to the questions that we just received.
Yes.
Really categorize the importance, the relevance, the significance of information in which include estimation problems and machine learning problems and even control problems, which would be something I think is very interesting as things like for people related to this topic. So that's the last comment.
Thanks for the comments.
Thank you.
Roy, do you have any questions or comments?
This is a very nice thesis defense. I'm feel lucky to be here. Going back to this question of the performance of the drone and the Y swarm, I was kind of surprised by your answer that the performance issues are really a function of the fact that the drones are transmitting this video. Because now I'm a little confused because when you think about getting rid of the queuing and doing kind of last come, first served kind of network interface, you think about that on kind of a packet by packet basis. But if you're somehow sending videos have lots of packets, and I'm not sure, maybe you're just burying some details, but maybe you could explain a little bit about how that works.
Very good question. And yes, we are hiding some detail. So what we did as a proof of concept, we sent unencoded video. So we were sending video frames. And when you do unencoded video, you can do last come first serve at the application level. So whenever a new video frame is generated, you can remove all of the video frames that need to go down to the lower network stack and put in the new video frame. And because if you're doing coded video, then you can't do this last come first serve because there is information between the video frames that you cannot remove. And you have to do something like first come first serve. So we actually kind of implemented last come first serve by using unencoded video, which also consumes a lot more bandwidth.
Okay. I have one more question, which is it's maybe about your last slide with CSMA, with different backup thresholds. Why is that A squared? Is that just an arbitrary choice, or is it motivated by some theory, or?
By trying to replicate the max weight policy that Igor proposed in his thesis, which was weight times A squared, and because that has nice performance guarantees. So if I do weight times H, then I will try to match something that does something like argmax of weight times H, but Igor's policy was argmax of weight times H squared. So I'm just replicating Igor's policy in a distributed way.
Okay, hey, thank you very much.
Sure, thanks.
Thank you all for joining us too. One more person on the call that I want to call upon, Nick Papas. Thank you for joining us. Are you right now in Europe?
Yeah, hi. Thank you.
Thanks for joining.
Very nice being here. Thank you for the nice talk. Yeah, it's a bit late here, and I have to speak low because my son is sleeping to the next room, so I have to keep my voice low.
Sure.
From my side, I would like to check a couple of things. Recently, I was also curious about the semantics, and I'm trying to work in this area. Of course, one idea, an age of information, is one of the relevant directions. However, I was, let's say, curious about if you try to combine the nonlinear aging functions with your drone application, and especially, I think the idea proposed by Professor Tsitsiklis that you have stochastic functions of age can be very relevant because this gives one more degree of freedom in that direction.
Yeah, I think it's a very interesting direction for future research. Just thinking of stochastic functions of age of information, and if you have some information about how they are evolving over time. And the way I think of it is, you can have two dimensions. One is age of information and some function over it. And then the function is also modulated by some context. And that context varies in a stochastic manner. And then if you have some model over how that context varies, then you can try to optimize over that.
Yeah, correct. Just to add something here that I find very relevant to this semantics, because at the end of the day, semantics is about, let's say, generating and transmitting less data without affecting what you want to achieve, right? And I think that the metric that was proposed recently by Professor Yates, that is also here, this version age of information can be very relevant, since actually, as long as you don't have change, maybe in the context, if we want to use this term, then you don't need really to, you don't age, then you don't need to transmit information. So this can be very relevant in this kind of tracking applications.
Yeah, definitely. I feel like, for example, for like caching, like the version age of information should be the metric that people should be using. It's precisely what we should be caring about. So
yeah. Great. Thanks.
Thanks.
Thank you very much for joining us. So now, I don't want anybody anymore in person, but certainly your questions are welcome. So any questions from the audience, anybody else? I was expecting a couple of questions to come from some of the students, especially the group members. Anyways, thank you. Thank you all for joining us. What I'm going to do now is I'm going to ask everybody but the committee to leave the room. I will ask Vishrant to initially stay in the room for close the discussion, and then chances are we just.
Sure. Can I do my acknowledgements or?
Oh, I'm sorry, I forgot about that. Yes, so before everybody leaves, the Vishrant wants to summarize, so.
Thank you. Yeah, so I wanted to give acknowledgements. It has been 6 years that I've spent at MIT, and yeah, a lot of wonderful people that I have met over the past 6 years. Most importantly, Professor Modiano. He has been the perfect advisor that anyone could have ever hoped for, and yeah. He gave me complete freedom to work on whatever I wanted to. I was never worried about the kind of work that I was working on, and he gave me the perfect atmosphere to work on problems that I wanted to work on. I would also like to thank my thesis committee, Professor Siklis, Professor Howe, Professor Polyansky. They always gave me very useful comments to improve my research. I would also specifically like to thank Professor Carlone and Professor Karaman. They were collaborators of mine during research. Professor Carlone helped us with the mapping project, with simulation, that Professor Karaman helped us with the drone project. Without his group's expertise in hardware, we would never have been able to do real experiments. I would also like to thank all of the collaborators that I've worked with over the many years that I've been here. Rajat, who I collaborated with a lot during my master's thesis. Our thesis was essentially a collaboration. Igor and Ezra, who were my co-first authors on the drone paper. We spent many nights working on that project, trying to somehow get it to work. Luca, who I also worked with Professor Carlone on the mapping project. Nick, who co-wrote the CSMA paper with me. Shahir and Alex, who were wonderful undergrads who wrote a lot of the code for YSwarm. Again, without undergrads, we would not have been able to write a lot of the code. And Wallabh, who has been working on an extension to our correlated problem with a very nice paper that is going to come out soon. Thanks to all the collaborators. I would also specifically like to thank 3 of my closest friends at MIT, Bai and Shinja, who came to MIT in the same year as me, and we spent all of our 6 years together, and Anurag, who was here in the group when we came. And yeah, we have done lots of things over the years, went to a Patriots game, went to Celtics games, done many things. This is us during our master's thesis graduation. This is us during their PhD graduation. I managed to do it